talking about migration based on the wave equation. Migration method, I said we have two methods. One's integral, one's wave equation based. Integral, we already said it before. Integral method, we divide into two methods. One is called control migration, which is your data domain. So you stay in the data domain, right? Another one, diffraction stack. You concede everything from the output from the model domain, which is geological model. Okay, so this is slightly different. Now, wave equation. Wave equation. We in this lecture will introduce you how to solve a wave equation. We knew how to form a wave equation, right? And then we need when we solve the equation in the migration context, typically for post-stack migration, we will introduce some one called downward continuation. That's also related to the physical principle. I will mention that later. And numerically, we use find the difference, which is Tx. T is time, X is space. So in the Tx domain, slightly faster, but you have involved more assumption, which is called Fx. We call it this explicitly find difference called Fx, and then further assumption involved will be Fk. So from Tx here you can mark here Tx domain. This one you can mark as a Fx domain. This one you will mark as Fk domain, of course. So just gradually becomes efficient, but more assumption involved. Okay, that we were talking about this thing, but also something else. Just talk about later. So, in the verification-based methods, you should always consider these three elements. You use a downward continuation principle. Downward continuation actually is not only in the seismic field, right? That's in the quite a lot wide field. For example, if you have an airborne, you measure, use aircraft to measure the gravity flow over the city of London, right? But you want to know if you measure gravity along the surface of London because so many buildings, right? You cannot measure that. So how you transfer your data acquired from the airborne to the data on the surface, that's called downward continuation. Numerically assume your aircraft fly not on the dark sky, but on the surface. That's called downward continuation, right? So the same principle used here for migration. Okay, so you have three elements. One is a downward continuation. Secondly, how to solve wave equation. Thirdly, when you solve wave equation, there's a very, very important thing called imaging condition. That's why we call it migration. It's an image, right? So imaging condition here, that's important. So always for migration, based on wave equation, there are always three elements you need to consider. Some terminology is different from analysis. Maybe one of these elements are different, but most likely the way you solve the equation is different. So when you talk about somebody say migration, use a wave equation, but they call different terminology, different name. Most likely they just emphasize the different way to solve the equation. Okay, nothing else. Right. For downward continuation, actually based on this principle, this is called the Huygens secondary point source. Right? This is a Dutch scientist. He's standing in the dam. He saw in the ocean there's a whale propagating through this gap here. In the inside, you can see the whale front looks like this, okay? So he's smart because he's a scientist. He thought, okay, if I move this bar, this is not a bar here, sorry, this dam, not at this position, but move to here, what it looks like. or move to here, what it looks like. Okay, so this is the Huygens principle. What he says is, all these waves here, each point of a wave front. So if we have a wave here, right? Each point of wave front can be treated as a source, all right? Secondary source. So for the one point of a wave, you generate this curve. But from another point, you generate another curve, right? So you can remember in the previous session, previous lecture, we're talking about superposition. We treat a reflector as a series of reflector, continuous reflector. We treat it as a series of diffractors, right? And the link that becomes, but here, it's not as identical to that one, but also assume existing wavefront can be treated as a series of new sources. Series new sources, right? Then each source from here, when wavefront hit here, you after that dam, you have a new wavefront. It's just like a point source. You see that? But this source is not the actual source, right? That's the original wavefront. One point becomes a new source. So for all the wavefront points, you have a series of new sources. That's the Huygens secondary sources. That's the principle, right? Now, he assumed you have a single point of wavefront, and then he assumed you shift, you visually shift, not physically shift the dam, right, forward towards your source point, towards your wavefront, what it looks like. So it was at Z0, so wavefront look like this. But now the dam here, you move towards your wavefront, right? When you move down to the Z1, from Z0 to Z1, the waveform becomes shorter, and to the Z2 becomes even shorter, and to some point, this becomes 1 point. You see that? Right? So that means any wavefront here, actually, you can think about this one is if a dam here becomes a single point, the barrier, single point of a barrier. You see that? So, right, that's in the horizontally, you shift the dam, shift the barrier, but vertically, in the subsurface structure, basically you move your surface downwards. Okay, you have a diffraction in the subsurface. You gradually downward your surface to the subsurface, gradually. Finally, your surface, the new surface, reach to that scatter point, reach to the front, wavefront. Okay, that's the image. This shows this illustration here. That's the surface. In the subsurface, you have a hyperbolic curve, right, which is a diffraction. Okay, so basically, if this one hit to the bar, hit to the barrier, if there's a small gap, that's become single point, right? Right, what he said. If we move this red surface downwards to green, this one from a gray becomes yellow, becomes shorter. You see that? And further down from red to green, even shorter. And then eventually, when the red reaches this point, it becomes single point, right? So you gradually collapse this diffraction curve into the single point. That's the mathematical implementation. Physically means you shift down your surface gradually down. That's called continuing downwards, right? Downward continuation. The curve is a hyperbolic curve. how do the downward continuation? So your surface was here, but now you moved to here, right? That means your wave field is different. So how to manipulate your wave field from the original wave field to the new wave field with a new surface, right? That's the practical implementation. Based on one thing called the wave equation. So wave equation here, same wave equation for all the wave phenomena, but the Z now is different, right? It was, say, for example, it was a 300 meter deep, but now we move by like a 10 meters, so now it's 290 meter, right? Or 280 meter, 270 meter, 200, and then gradually to the 10 meter, and then 0 meter. You can see they use the same equation, but Z different. Okay? So this is the way to the downward continuation. Okay? This is the wave equation. I said the wave equation is nothing more than the two principles, F equal to ma. Right, let's see. F on the right hand side, but here, if we next to the source point, we have a force. But apart from source point, you do not have, no longer have force, right? You only have strain. A stress, sorry. The particle shifting stress, all right? So usually, apart from source, in the source point, we put source here, but most likely we put 0 here, okay? M is a material. M is a mass, right? Density. But if we assume in this case acoustic density is constant, so we can delete the constant rho. Ma, this particle, this pressure or particle movement, that's second order of a derivative, which is acceleration, right? Fourth order derivative is velocity. Second order derivative is acceleration. F equal to ma, right? M is density we canceled. A is this term here, right? Hooke's law tells you strength and stress relationship. So the rest part here, in fact, is the coefficient between strength and stress, okay? We just simply call it. After all the simplification, constant, isotropic, you end up only of this term here, right? That's actually related to the Young's modulus, lambda mu, but it's simply called velocity, okay? In the seismic, when we're talking about acoustic wave equation, we only consider consider the velocity. Okay, this came from there. Now, issues with wave equation. We have a wave equation, and we know the same wave equation applied is applicable to all the different depths of a downward continuation, right? But how to solve wave equation? First of all, the wave equation is a second order partial derivative. It's difficult to solve, right? Because the second order means if we talk about something quadratic squared, means your positive number squared equal to negative number squared, right? So minus a squared equal to positive a squared. So that means you have two directions, positive, negative, two directions. So that in the equation, there have two ways. One is called upgoing energy, one is downgoing energy. So you also need to make a decision which you take positive value or negative value, right? So that's two issues, okay? So one gentleman is very smart, called John Clabert, is from University of Stanford, American University. The gentleman retired. He came up something, okay, I forget about math. He just come out something, even high school teacher will give you a 0 mark because it's totally wrong, but practically works, okay? He solved the second order wave equation. What he did? He solved the second order equation just like he just treated second order derivative as a second order of a variable. And he just do a crude square root. Okay, mathematically definitely wrong. Okay, this is but practically works because this gives you a positive, negative direction. So that's the code. You can select one direction. Okay, let's see the detail. That's just actually that's two fundamental mathematically two fundamental issues. One, the square root of a second order derivative. That's not mathematically right. Secondly, it depends on the for the second order derivative is not able to do the Taylor expansion. Right? Taylor expansion we never say how to do the Taylor expansion of a derivative. Right? We always say the Taylor expansion of a function. Just well, he's great geophysicist because he can do everything, beyond the imagination. That's gentleman published a book in 1976. What he did. That's for the downward continuation. This is verification. For downward continuation, he's okay. Forget about the verification itself. What he did was this. If we're talking about first order derivative, wave field downward continuation means in the z direction. This one, first order derivative, which is a continuous function, equal to this term minus term divided by delta z, right? That's we call the final difference. So at depth z plus delta z, which is a dipper, minus the wave field at the depth z, and divide by the delta z. This approximation of this continuous function of a continuous function, first order derivative, right? So based on this one, the downward continuation is this. Okay, that's for downward continuation. And for this downward continuation, you need to know first order derivative, right? Because you know the wave field at the current depth, maybe z equals 0, which is on surface. You record the data on the surface, and you also know the downward continuation step length, which is delta z. But in this equation, you only don't know this one, the first order derivative, right? If we know this, you can solve this. But how we solve this based on the wave equation, this is his trick here. How to solve the first order derivative based on the second order wave equation, second order differential equation. That's his trick. But he actually did it this way, but he didn't say it that way, okay? I'll give you this, as I said, I try to give you the physical meaning. What he did. He put this original wave equation, the Napla squared becomes, for the two-dimensional becomes squared, second order derivative of x, second order derivative with respect to z. But if it was three-dimensional, you have a derivative with respect to y. But here we just x and z. If you move this one keep this one in the left-hand side, move everything to the right-hand side, you can see the second order derivative equal to the wave field at z pre-multiply the wave field multiplied by this operator. We just simply call this operator, okay? He said, okay, you want a first order derivative? I'll give you a first order. What he did is simply do the square root of this because he thought this was a square. Second order derivative is not square, right? But he just, okay, I just treat it as square. That means you have square root. Square root means you have positive, negative, you see that? Physical meaning means if this is positive means your variation along the z. Negative means your variation along the negative z, right? So that means down going, up going wave. Okay? Because you do downward continuation from the surface downwards, so basically positive z here is the wave field you want, right? So he end up for how to solve the equation. He used this way to solve the equation. That's his invention. Okay, you consider only downgoing wave, right? However, even he has made such brute, crude assumption, which means he can square root of a second order derivative, right? That's mathematically not right. Even so, we still have trouble here. What trouble? Because there's a square root here. The square root, we don't know how to solve it, right? So that square root, we can use Taylor expansion. Again, we'll do the Taylor expansion based on the functions, but not the second order derivative operator, right? But he tried to do that. What he did, he transformed your time variable, which is time variable, second order derivative, into frequency domain minus omega square. Here, that's positive, but it's become minus. It's also minus, all right? But then that becomes a minus square. So here, minus I square, and then you put in the front. That's actually accurate formula, okay, from previous one. You just do the Fourier transform with respect to the time. That's the formula. Now, if we do in the frequency domain, it was Tx domain, right? After the Fourier transform becomes Fx domain, or omega x domain. Omega is 2 pi f, right? So if we do this, the square root becomes two terms, we call the first order, or in here basically squared, we call second order. That's the second order Taylor expansion, truncated as second order. Or you truncated as fourth order, right? Let's go back to this formula, that's square root. So 1 plus x squared and the square root. You do the Taylor expansion, you end up this one, 1 plus this one, or 1 plus the squared and the fourth and the sixth and the eighth, right? Okay. For this one, we simply call it 15 degree, and this one called 45 degree, and then you can have 60 degree, but never be 90 degree. Okay, how to do the degree? Let's see, because if we want the Taylor expansion available, remember, when we do the Z transform, we're talking about inverse field, 1 plus or minus x, the x should be smaller than 1, right? Otherwise, the Taylor expansion will not converge, okay? So this means, this formula, if you think about the cosine square, the angle here should be less than 15 degree and 45 degree, okay? So this is the way. I do not derive here, but just we will observe this from the result, from impulse response, okay? Now, so how to solve that equation now? We already do two things, right? One based on the first order derivative, we have a downward continuation formula. Secondly, because in the downward continuation formula, we need a first order derivative. Now second part, we transfer the second order partial derivative equation into the first order, but we take a positive direction, right? We take a downward wave. Now, in how to solve that formula, how to solve this formula, have a second order, right? How to solve that? You basically, if you solve that, you have a final difference way. We call it final difference. So first order, you have just simply time difference divided by the wave field at different time divided by the time difference, right? The second order, you do the one more time, you get second order. For the spatial direction, you also have similar formula, basically p minus 2 and the plus 1 minus 2 and p. That's the tensor for the final difference. Okay, so this is the way to do that. If we're talking about final difference method. So this, because here we use the t and the x, so this solution here is in the Tx domain. Let's emphasize that, okay? Generally, in the Tx domain, we just call the finite difference method. But the finite difference method, we already mentioned a 15 degree or 45 degree, even you can have a 60 degree, okay? For the finite difference method, at least we solve finite difference equation, you have two ways. One is called explicit method, means you, on the left-hand side, is a new solution you want, the new point, which solution. On the right-hand side are all the elements you already know. So basically, you, based on everything you know, derive the new solution. This is called explicit method. Or you mix them as a quadratic, or in this case, actually, yes, quadratic. And not in this case, linear equation, but you resolve it. You just do the inverse. That's called implicit method, right? You have ax equal to ax plus b equal to 0, or ax plus b, x squared plus bx equal to c. You can solve that. You solve this way, right? That's called implicity. But two methods have different effects numerically. First of all, this one explicitly because you accumulate the known results. So any errors in the previous step will be accumulated into the new solution, right? And then numerically, when could be not stable, some errors will be amplified and cause the system unstable, all right? Implicitly, actually is uncontinuous but always stable, because basically just like inversion, you always try to fit a solution to the current equation, right? It's always stable, so uncontinuous stable, right? So this is the difference. However, because implicitly you need to solve equation. For single equation, fine, but for a huge system, you have a system equation, maybe 300,000 unknown variables. That means you need to solve the huge linear system equation, right? So the computation is more expensive, right? That's the difference. For the final difference, let me just summarize 3 issues here. We already talked about 2 issues with the third one. First one, accuracy. Accuracy. Implicit method is much accurate than explicitly. Explicitly can accumulate and also amplify errors, but implicitly more accurate. However, the accuracy also depends on the final difference operator used, delta x and delta t, right? Because the original wave equation is a continuous form. So if you do the discretization, you always have errors, right? So this accuracy also depends on the delta x, delta t samples, okay? And the stability, as I said, implicitly is uncontinuous stable, but very, very expensive. And explicitly is not that stable, but you may use some constraint to make it stable, right? But maybe you sacrifice something else, okay? The third thing is called dispersion. So that means delta x and delta t is not arbitrarily, either of those are not arbitrarily designed. You must follow something. What's called the dispersion here means numerical dispersion. Numerical dispersion means, okay, because when we discretize model, delta x and delta t, these 2 elements are orthogonal. Orthogonal, okay? So that means orthogonal means one vector along the x direction, another vector along the z direction. When you do that cross correlation, there should be 0. Okay, x direction and z direction, so the cross correlation should be 0. This is orthogonal, so 90 degree. However, subsequent wave travel not necessarily either 0 degree or 90 degree, right? They travel around a different direction. So you only know the horizontally, only know the vertically, but you don't know actual angle. right? The aperture angle is a square root of horizontal velocity and the vertical velocity, okay? So that means your velocity is travel depends on angle. This angle dependency will cause numerical dispersion, okay? That's the thing. So I didn't show the image here. Eventually, if you expect to have a perfect circle, but it comes out like a diamond shape because horizontally right, vertical right, but in the absolute direction, not right. Okay, that's the dispersion effect. As I said, we have three elements. One is downward continuation. For downward continuation, that's actually quite straightforward. You know, ideally, we use the delta z. That's called the depth migration, right? However, we don't know exactly the velocity. Okay, we don't know exactly velocity. So more practically, a more practical implement is you use time rather than z. Okay, so if velocity have like a 10% higher or lower than the true velocity, you still have a good image. So in theory, it's a depth migration, but in practice, it's a time upward. You upward delta t rather than delta z. Okay, that's the one thing. For the depth migration, you can handle lateral velocity variation. So that means because you only do the delta z, right? Within this delta z, laterally velocity can variable. Velocity can be variable, right? Laterally. So this one can handle with lateral variation. Okay. For the depth migration, for time migration, you always assume velocity locally is constant. But for the depth, you can assume velocity is not constant. Okay, that's the difference. Because depth migration exactly follows physical wave equation, that means you follows the Snell's law, follows ray bending. Snell's law means instant angle to the reflection angle or transmission angle, right? That's the Snell's law. But for the time migration, does not follow Snell's law, okay? They're banded. So, however, the advantage of time migration is your velocity. If you have some velocity variation, the migration will not be so sensitive. If sensitive means maybe your migration is not stable, okay? So that's the positive negative thing compared to. So most likely for your data processing, you actually implement this one. You can see you can have a velocity not right, but for geological implementation, you also have trouble, right? That's not a true physical principle. Right. For every equation, I said we have three elements. We already said the downward continuation. Downward continuation, we need a one-way approximation to solve the equation because otherwise we have a second-order derivative, right? And the third element we mentioned called the image condition. What the image condition means, they're called exploding reflectors. Same principle like a Huygens principle. What that really means, that means in the Huygens principle, we assume each element in your wavefront is a new source, right? In the migration concept, they said that each point in your reflector is a visual source. So you do, for example, you source point here, if I measure here, you receive the wavefront. But if you move your receiver plane, you receive plane towards your source, which actually is not a source, it's a reflector. You gradually focus to the reflector point, right? So the same principle. But again, same gentleman, John Clapott, he said, we just assume your subsurface structure is exploding reflectors. So that means you have dynamites at every point of your subsurface structure. And they boom, 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 right? And then you received at a certain distance, but you move down, you downward continue your surface gradually towards the reflector, which means your travel distance 0. And that focus point is a reflector, right? This is the principle. So image condition now. We further explain that. Image condition assume this exploding reflectors. You have a dynamite along the reflector every point, right? And this have a strong proportional to the reflection coefficient because you focus into this point. This point reflection coefficient is different for other points, right? So this is actually better than the diffraction stack. Diffraction stack ignore the reflection coefficient variations, but this is better. Okay. However, because you downward from a surface from a exact surface down to the reflector, but your travel time, ray pass is two-way time, right? From source down here and go back. But now you assume the exploding point at the surface, so you travel distance halved. But in this image, you don't know the travel distance. What do? You just half your velocity. So in the migration, you same equation, but velocity multiplied by 0.5. You do the migration, half the velocity. Okay, that's the one thing here, one parameter. And the image condition, this is the image condition, t equals 0. Straightforward, very simple. I will explain why it's called t equals 0. Because t equals 0 means you have a dynamite source at that time equals 0. So what you try to image is go back to original time. That's so image condition t is 0, right? Mathematically, you will see if after Fourier transform, t equals 0 is a DC components, right? That's mathematical term. But for the physics term, for migration, t equals 0 means actually the point, so the exploding point along your reflector. Let's see this one here. This is a zero offset. This is a subsurface structure. For this point, maybe you have this point here perpendicular to the structure, okay? But you assume there are a series of explosion points here. You try to downward continue surface, downwards. If you reach this point, you have this one, just come out, t equals 0, right? And the further down, you reach to here, and then slightly downwards reach to here, right? So this is the principle. His book, you do not necessarily go to the library to borrow a hard copy online. You can find this book from his, well, before he retired, he was in the Stanford University. So there's a book over there. Exploding reflectors means everywhere you propagating wave upwards to this point. So there's only single ray path. So what do you need? One parameter. Actual velocity, you after an MO, you have velocity for migration, right? But every velocity value you should divide by 2. Use this velocity to the downward continuation, okay? So in your original seismic profile, after stack, you have a X and a T, right? So this profile is recorded at the surface, Downward continuation means this profile, you downward to the next step, delta Z. So you go to here, image. Because you downward, so X is same, but Z slightly short, T slightly shorter than the original T, right? T and Z is same, as I said, because of velocity sensitivity you prefer in the T. Okay. Now, another delta T, downward continuation, another delta T, another delta. So that means it was a profile, 2D, 2-dimensional, but now becomes a 3-dimensional cube, right? That's not the image. However, John Kleber told us, you assume the reflector is a series of exploding points. That means t equals 0. So for each of this image, you just take a t equals 0. Take this, take this, take this, take. So this one, now you have X and a Z. You can see that's the image. Image have X and a Z. So all the image you taken was at time t equals 0. That's it. Okay. So, but in the processing, you do need to keep this whole profile for the next data t. Keep this profile for next data, but you output only t equal to 0. That's the principle. Okay. So web equation method I already mentioned. Based on the web equation, we use a downward condition as element 1. We use an image condition as element 3. Between 1 and 3, the second element is how to solve the equation, right? As I said, 3 elements for web equation. How to solve the equation based on the data format, based on the web equation format, originally was in the TX domain. So we used to find the difference with a second order final difference, right? And then we use, if we assume the variation along the time is not so strong, we can do the Fourier transform. So we have a fx. And then if we assume not only f time domain, time axis variation not strong, but also assume that spatial domain, spatial axis variation not that strong, you can transform x to k. So you can from a tx to fx to fk. Right? The efficiency gradually increased, but more assumption involved. Okay. And in terms of in my opinion degree, this one maybe 15 degree or 45 degree, but this one can have a higher angle, but this one principally can up to 90 degree. Okay. Let's see the first method, find a difference method in the TX domain. Okay. This is also invented by the gentleman, Professor John Clabert. He published a book in 1976. So they use find a difference in time, also find a difference in space. However, two-way equation was approximated to one-way equation. Okay. This is generally find a difference method that was only 15 degree. And then 45 degree one-way student invented. That's a stack section. We saw this before. We have diffractions here, right? We have diffractions here. The find difference migration. Have this, your order diffraction collapsed, right? Collapsed to point. And then you have a small syncline or somewhere anticline, but not big. Typically, you have some fault here. But you see this fault is not as clear as the previous Kirchhoff migration because this one may be up to the 45 degree, right? That fault may be higher than 45 degrees, so you do not see that better. But this, in terms of signal to noise ratio, that's good, right? You do not have like a so-called, like over migrated so-called in the Kirchhoff migration, right? But here you can see you have a very nice signal to noise ratio. Compared to Kirchhoff migration, the advantage was Kirchhoff migration, you can have this fault clearly because Kirchhoff migration can migrate up to 90 degrees, even over 90. But go back to this one, for this steep dipping events, this method cannot handle it, right? Okay, but in terms of this one, Kirchhoff migration, you do have any point here becomes a circle. This over migrated, right? But for the Kirchhoff migration, you have a good image. You see positive, negative, right? Advantages, disadvantages. Now let's see about the degree. Okay, final difference migration. I said maybe this 45 degree, right? Come out for that degree, but you definitely cannot migrate anything like 90 degree or anything close to 90 degree, okay? So this will be illicit here. You can see here it's illicit. If we do the anti-aliasing mute, basically you have only this part. But for the kitchen micron, you can see have the stippling like look at this, even this over 90 degree, you can see that. Okay, so this so-called impulse response means you do the migration for whole seismic seismic profile, but actually only central trace keep the as original, or other traces will mute to 0. But you do migration. This is called a migration impulse response. This impulse response gives you an indication of a migration degree. Okay. That was TX domain. After Fourier transform, with respect to time, we came to the FX domain, right? But in the original paper, they called it omega X. Omega X, okay. Omega X, why they call omega? Omega equal 2 pi f, right? Which is angular frequency. Why they keep that? Because they want to try to keep the k, which is a wave number, as a 2 pi. How many circles per meter, right? So this indicates next step when you do the k, it's not like 1/meter. It's how many circles per period, right? That's omega x. You just think about fx, okay, same thing. So you just do the one Fourier transform. In this way, this was invented by a Calabos PhD student. It's this gentleman. What he did, in the space axis partial derivative, they use the time difference, but in the time axis, we do migration, right? Step by step, with delta t by delta t. He said you do not need it. You just do the all in one go in the frequency domain. In the frequency domain, you see that? Any operator, we can treat as a filter, right? What a filter really means convolution in another domain. You see that? So the downward continuation basically is a convolution in the depth or convolution in time. So what if we do the Fourier transform? If we can recall that, Fourier transform of a convolution means multiplication, right? So you do not need a step-by-step convolution, but you just do the convolution multiplication, so it's much faster. Plus Fourier transform much faster. Use the FFT, fast Fourier transform, right? You can see the efficiency increase by dramatically. Okay, so that's the space domain still use a convolution, which is find the difference, but in the time domain, after the time domain, Fourier transform use a temporal frequency, so the convolution becomes a multiplication. Okay, but this one up to 45 degree accuracy. Okay, let's see the example here. This FX find the difference, still called find difference. This method. You can see here the dipping events gradually come out because this one can up to 45 degree. Previous one only up to the 15 degree. So that's gradually come up, all right? Okay, but very, very efficient. Compare the final difference you can see here from a TX domain to FX domain now. The issue with the final difference, first of all, there's two methods. That's a 15 degree or 45 degree accuracy, right? Not as good as a Kirchhoff migration. Numerical dispersion, this limits your delta t or delta x. And the stability, right? Numerical stability, because if we do explicitly, that means accumulate noise, accumulate errors, end up divergence, right? So also another thing for 3D case, I do not talk in this lecture, but also have azimuthal anisotropy. So velocity not, I said the velocity anisotropy means depends on the propagation direction, but also depends on the azimuthal angle. That's in 3D case. But here we're talking about 2D only. Right. That was a final difference. For the FX method, you similar to find difference, but in the vertical axis, you use a modification of a temporal frequency rather convolution, right? And otherwise, same in the spatial direction, you still use a find difference operator. Find difference operator means you do the convolution along the space, okay? This example we show you here. That's the FX domain result. You have this one, but why I show this one here? You can see something here. Just a water bottom. Just a water bottom, but we have something in the front. This is the indication the seismic trace in the processing has been transferred to the frequency domain, and then after processing, transferred back, right? What's this called? That's right, wraparound. So because they try to save in computation time or space, they didn't have enough padding in the vertical axis, okay? Impulse response, I said this one can up to 45 degrees, you can see here steeper, but the final difference is a slight different, right? So, but this bit is anything, but this one 15 degrees, okay? So this difference. Finally, before we dismiss, another one, further substitution. We assume velocity horizontally also constant. So that means you can do another Fourier transform, which is a two-dimensional Fourier transform, not only f, but also k. We learned the fk transform before, right? In this case, both direction, instead of convolution, both direction becomes multiplication. That's very simple, right? This gentleman from I can't remember. It's from Eastern European, from Slavic, I think. So Fourier transform in both directions, and we learned this before in the FFK domain. So the dipping angle in the TX domain becomes a K to F ratio, right? This follows Snell's law, but divided by 2 because the velocity will be halved. Remember, yeah. So in the downward continuation, if you recall that, downward continuation is the final difference of the fourth order derivative. So x, z, t. So now after Fourier transform, x becomes kx, t becomes omega. Right hand side, this shifting operator becomes this phase only. I omega, I theta here, that's phase only, okay? That's called a phase shift. So phase shift accurate to 90 degrees. And as I said, if you guys can invent for the two-way time, that means you can do 180 degree migration, right? You can see here up to 90 degrees because it's only one way. Okay, this is exactly for vertical velocity variation. So people say, okay, I do this first and then you do the correction. That's quite a common practice if the velocity variation is not strong. Result, right? That's the phase shift migration. This can up to 9 degrees. So all the dipping fault here is much clearer compared to previous methods. And see, find difference. This dipping event not appear, right? This the phase shift image impulse response. That's 90 degree, up to 90 degree, but nothing more than 90 degree, right? But up to 90 degree here, still not the earliest. That's the final difference, only 15 degree. Okay, so in general, migration. So migration involves approximation. That's for steep dipping events, okay? And the phase shift is it's a very good one, up to 90 degrees. Vertical migration can handle velocity variation. That's good, but the difficulty is for the anisotropy. And in the ray tracing method, control migration, this one's easy to handle, this one not. However, the amplitude in this case is much more accurate compared to the control migration, okay? So that's the advantage. For seismic data analysis for AVO immersion, for reservoir prediction, you prefer to use data generated by this method rather than textual migration method. Okay. This is what we learned today. Based on the observation of modeling, we come out to migration idea. And based on the observation, we come out to migrate the equation. Simple, sin theta equal to tangent theta, right? One's the model space, one's state space. For different method, we talk about a two integral method, diffraction stack, textual migration. Also, we talk about verification method, right? Verification method have three elements: how to do the downward continuation, how to do the imaging in between, how to solve the equation, right? So that's it.